chart. So this is about the pH chart. So that is about the pH chart of this one. Next, we will move on to the another chart. So that is the temperature versus enthalpy, TH chart, right? So here also a student has to observe that what are the things: temperature versus volume, temperature versus entropy, temperature versus enthalpy. So the things where a student has to understand this particular thing, connection between this one. When I talk about the temperature versus in this one, so immediately student has to get is what are the planes. So here also you can find out the three things, that is temperature versus volume, temperature versus entropy, temperature versus heat, that is enthalpy, temperature versus enthalpy. See, on a temperature versus, this is slightly slanting towards the right. This inverted U shape is slightly slanted towards the right direction, and these are nothing but the constant pressure lines representation will be like this one. The constant pressure lines representation will be like this one, right? So at the critical point, the enthalpy of evaporation is equal to 0, right? So here you just observe the HFG. This is the HF, this is HG. This is HF, this is HG. This is HF, this is HG, right? So at the critical point where the saturated liquid line, saturated vapor lines are going to merge, and at that state, enthalpy of evaporation is equal to 0. So it is a temperature plot versus enthalpy for substance during the phase change. It helps to understand the relationship between the temperature, that is this is the T temperature, right? Temperature, and the heat content during the melting or solidification. So this is the heat content, that is enthalpy. So property diagrams provide a visual representation of the thermodynamic properties, visual representation. That means what is the value of HF, what is the value of Vg, what is the value of SFG. So that is. So it is a thermodynamic properties of a visual representation of the thermodynamic properties of a substance during the phase change process, and is used in a wide range of applications, including the energy systems, refrigeration, industrial purposes. They help to understand the behavior of the substance during the phase changes, which is crucial for optimizing the energy systems and industrial processes. So that is the significance of usage of this particular PT diagram, or whatever it may be, the diagrams are there. So that diagrams a student has to understand onto this particular site. So this is what a type of this one, temperature versus enthalpy line. Next one is the temperature versus enthalpy. Generally, when the question is going to ask, that is explain the phase transformation of a pure substance. Explain the phase transformation of a pure substance. In that case, try to visualize this particular temperature versus enthalpy diagram and the temperature versus volume diagram. Temperature versus volume diagram. So what this is going to indicate, temperature versus enthalpy, or the TH diagram. Just now it is also covered, right? So I will show you a slight little bit difference between the TQ diagram and the TH diagram. That is the temperature versus enthalpy. So temperature plot versus heat of a substance during the phase change, it helps to understand the relationship between the temperature and heat content during the melting or solidification process. Generally, the property diagrams which provide a visual representation of the thermodynamic properties of a substance during the phase change process, right? Next, the temperature versus volume diagram. So it is a graphical presentation of the relationship between temperature and volume of a pure substance. Volume of a pure substance. But anyhow, whatever it may be, the property diagrams are there. So that property diagrams are going to give the information on the realization of a the enthalpy realization of the properties of a pure substance at various locations. So here, let me to observe this onto this particular side. So temperature versus if you just take the this is the temperature and this is the heat supply right? So first initially the ice so this is the sensible heat, and after then this one, that is the sensible heat, this one. So in this case, two things which are going to be getting over here, and if you observe this particular thing, so there is a sensible heat of fusion, latent heat of fusion, right? Two terminologies are there. See here, sensible here I am talking about the heat point of view. When you convert the ice at -5 degrees centigrade to steam at 300 degrees centigrade, then what are the things are to be considered? Sensible heat of a fusion plus latent heat of fusion. Next one is sensible heat of evaporation and latent heat of vaporization. Evaporation or vaporization, both the things are same. Sensible heat of vaporization, latent heat of vaporization. So these two things you have to consider. Next one is the superheat. So the next point is superheat is to be considered. So in this case, two things are going to be getting here, and this is nothing but, this particular line is nothing but the superheat. This particular line is nothing but the superheat. So that is the superheat. Superheat is nothing but the temperature of a liquid is greater than the saturation temperature of the vapor. Temperature of a liquid is greater than the saturation temperature of the vapor. Right? So these things a student has to observe. Now onto this side, if you want to apply the sensible heat, that is Q is equal to mCp delta T is to be applied. mCp delta T. To this side, Q is equal to m into latent heat of fusion, right? So let me write it as a latent heat of fusion, right? So here also, that is in the case of a sensible heat, so here also that is Q is equal to mc delta T, and for the case of latent heat of evaporation, so here also Q is equal to m into HFG. So these things you have to apply here. So that's why I'm calling this one as the heat. Then what about the TH? That is, this is the temperature and this is the enthalpy. So it is the inverted line, and the constant pressure lines will be of this one. Constant pressure lines will be of this one. This is the critical point. Right? Constant pressure lines. So this is how the temperature versus entropy. It is if you once again recapitulate, or if you once again observe this particular thing, then you can get the importance of this TH plane. So that is the basic difference between the TH plane and TQ plane. So observation of the TQ plane and the TH plane, little bit difference is there. So that a student has to identify that particular difference. So let me show that TH diagram once again. Yes. Now you can observe here. This is the temperature versus enthalpy, right? And temperature versus Q, that it is already shown into this side, right? So that is one way. Next, there is another one is that is temperature versus the volume. The temperature versus volume. How you can represent the temperature versus volume for a phase transformation of a pure substance. So let me show that one. The temperature versus volume. So this is the temperature versus the specific volume or volume. So suppose here, if you take the water, solid ice. So in that case, the solid ice first at -5 degrees centigrade to this one. Then after the another curve which you will get here as in this one. Then after you will get the another curve which is of this one. Then you can get the another curve that is of this one. So in this case, if you just observe that there is a -5 degrees centigrade. So if you observe that this is -5 degrees centigrade, right? And this is 0 degrees centigrade, and this is 4 degrees centigrade, right? And this is the 100 degrees centigrade, and this is the critical point. And at the critical point, the temperature is 374.5 degrees centigrade, right? So that one has to understand this one. Now you observe the volumes here. What about in this change? The volume is increased. Then conversion of 0 degree centigrade to the 0 degree centigrade here, what is happened? The volume is decreased. So here volume decreases, and here volume is decreased. And from there, from 4 degree onwards, whatever the heat you are going to supply, it is continuously rises. So this is what anomalous expansion of a water. That means from 0 degree centigrade to 4 degree centigrade, what is going to happen, right? So that means here the water gets expanded. Whereas the other substances like carbon dioxide, the other substances are going to be gets contracted onto the freezing. Only the water is going to get expanded into the freezing. So that particular things student has to observe. And this particular portion, it is nothing but the liquid, and completely of this one here to the outside of this one, it is the pure substance is going to exist in vapor phase. And within this dome shape, the liquid plus vapors are there. And in between the dome shape, you are going to find out the HFG, SFG, UFG, VFG, right? So this is all. At this case, you are going to find out the VG and SG and HG, UG. And at the left side of this dome, that is onto the line, you are going to find out UF, SF, HF, and SF, right? So these things where the student is going to make the calculation for this particular point of view. So that is what the meaning of the property diagram. What is the significance of this property diagram? So all these particular things, it is discussed over here. All these things are discussed onto the property plane. So once these things are over, then the PV plane. So PV diagram is also there. So that if you just once again go through that one, the PV diagram, onto the PV diagram of a pure substance, this is the constant temperature lines. These are nothing but the constant temperature lines representation. See here, right? So PV diagram, this can be used to determine the work done by substance. So when we think of, or when we made a discussion onto the pressure versus volume, automatically one parameter, that is the work done, it is the area under this particular PV plane is going to give the work done by the substance. So the change in internal energy and other thermodynamic properties, that is the usage of the PV plane. The general shape of the PV diagram of a pure substance is very much like TV diagram, but T is equal to constant lines on this diagram are downwards. So this one are downward, right? So you can make the discussion. If you can place, you can make the discussion of this particular PV plane. Say suppose if you can take the piston cylinder arrangement, and where this is the piston, this is the piston, and this is the cylinder, and if you keep the water here, if you keep the water, right, and here you place some of the incremental weights onto this one, go on adding, go on removing that one, so that the pressure inside, if you go on adding the weights, the pressure is going to increase. If you go on removing the weights here, the pressure goes on decreases, right? So that type of a discussion where you can get from this particular side. So this is all about the PV diagrams. So the various varieties of a PV diagrams are there. So you just think of the content what is mentioned here. So try to go through that particular contents, and the enthalpy, how you can find out. That is already we know that the enthalpy is nothing but equal to H is equal to U, capital U plus PV. Then what about the small h? This is U plus PV, and this is all in kilojoule, and this is all in kilojoule per kg. This is all kilojoule per kg. So on this context point of view, this in pure substance, this H is going to exist as HF, HFG, and HG, right? So this V is going to exist as VF, VFG, VG. So that things you have to observe here, and related to this particular thing, a student has to explain this particular content. So these are the various PT diagrams, various property diagrams. So in the same way, the compressed liquid is there, when we can call it as a compressed liquid, and when we can call it as a quality of a steam. That is here the quality of a steam. See, this is the quality of a steam. That is, this is the quality of a steam. So how you are going to find out the cases? So if you want to find out the volume, then V is equal to Vf plus X into Vfg. Vf is this one, Vf is this one, or Uf, or Hf, or Sf. Whereas this one is Vg, Ug, Hg, Sg. And in between this one, you have to apply. That means you have to apply within this dome shape. V is equal to Vf plus Xfg, U is equal to Uf plus Xfg within this dome shape, where X is nothing but the quality of a steam. S is equal to Sf plus Xfg. So this is how a student has to apply for making the calculations of this particular thing. And one more point that I need to discuss, that, say for example, at 1 atmosphere pressure, the latent heat of fusion of water is standard value. A student has to remember it as the standard. Latent heat of fusion of ice is 333.7, whereas the latent heat of vaporization is 2255.5 or 2256 kilojoule per kg, right? So at below the triple point pressure, substance begins to change directly to the gas. Enthalpy of vaporization, see here, enthalpy of vaporization decreases as the temperature and pressure increases and becomes zero at the critical point. See, at this case, enthalpy of evaporation is 0 at the critical point. So the superheated vapor condition is there, right? So after observing this thing, some of the things which you can highlight to this particular side. So that is so far what you have observed. Different significant lines such as saturated liquid line, it is observed, saturated vapor line. Now you have got isobaric line, that is constant pressure lines, isothermal lines, that is constant temperature lines, constant specific volume lines, constant dryness fraction lines. These are shown onto the Mollier diagram. So the Mollier diagram is nothing but it is the representation of the enthalpy versus entropy. Enthalpy is on y-axis, entropy is on x-axis. So the nature of variation of the different lines can be explained from the real behavior of a substance and the mathematical expressions based on the combination of first and second laws of a thermodynamics. So when you study the Mollier diagram, there are two questions are going to rise onto this side. What is that one? Why the isobaric lines diverge from one another? Why the isobaric lines diverge from one another? What is the reason? And this is due to the increase in saturation temperature with increase in pressure. So the slope of isobar is equal to the saturation temperature at the beginning. Therefore, it also increases with the increasing pressure. The another question which you can make onto the Mollier diagram is that isothermal lines are not visible in the wet region. What is the reason? It is because constant temperature lines and constant pressure lines coincide upon in the wet region. So for every pressure, there shall be a definite saturation temperature which remains constant in the wet region. That means if you are showing the constant temperature line, pressure is hiding. That is the pressure at the back side of that particular line. If you are showing the constant pressure line, the temperature is at the back side. That is, it is in a hiding condition. So that's why these things are, only one is visible, and automatically you have to think that the other line is also onto the same line. So that is this particular thing, right? So this completes the property diagrams. Hope I have covered all the things. Hope I have covered all the things related to this particular matter. Okay. So now, thank you one and all. Thank you for patiently listening this particular lecture.